Bash programming lecture. One of the most powerful features of the Bash scripting language is how one can combine commands. And combining commands is really one of the core concepts of the Unix ecosystem. Unix consists of a bunch of very simple commands, and by combining these commands, one can generate very powerful operations. Often you find that Bash commands and Unix applications in general only solve one relatively simple task. But they solve this task extremely well. And one can combine these commands by using text as input and output for the commands. I want to show you a simple example. Imagine you're faced with a task to write a script that prints today weather forecast in Oslo. Think of a programming language of a choice and how you would implement that. In Bash, the solution is a single line of code. If you run this command, you can see that today the temperature is 18 degrees. It feels like 18 degrees for 7 o'clock tonight. We will re-implement the solution tomorrow in our interactive session. In order to understand how to combine processes, we need to understand the in and outputs of a single Bash process. And there's 3 of them. There's the standard input, standard output, and the standard error. Each Unix process takes user input through the standard input stream, typically from the keyboard, and it outputs normal information through the standard output stream, typically on a screen, and it outputs error information through the standard error stream, typically also on the stream. The trick to combine multiple Bash commands is to redirect these standard streams to different commands. This picture shows an example where we combine 3 programs with each other. Program 1 takes the user input from the keyboard and it passes its output through the standard output channel into the standard input channel of program 2. The standard error stream is redirected to the display so that the user can see potential error message. Program 2 also displays the standard error stream into the display, but it passes the standard output stream to the standard input stream of program 3. Program 3 passes the standard error and the standard output stream to the display so that the user can see the results. This concept of connecting standard output and standard inputs of 2 programs is called pipes in Bash. And the syntax is this vertical line here. So by using this vertical line, you connect the standard output of a command to the standard input of another command. Let us look at a simple example. Let's say you would like to see all the Jupyter Notebook files in a directory tree. You can use the ls command to show all files in a directory tree. Jupyter Notebook files have the ending IP, Y, and B. And you can see there's a lot of files that are not Jupyter Notebook files. So I use a Bash pipe into the grep command. The grep command filters lines that contain a specific string. In my case, I want to filter lines that contain the .ipynb line. And if I now execute this command, you can see that I obtain a list with all the Jupyter Notebook files. Let's look at another example. For the grep command, I want to find options that can control case sensitivity. I use the man command to show me the manual of the grep command. It is a long document and I'm too lazy to find all the details about case sensitivity. I use a Bash pipe and use the grep command itself to find all lines where case appears. Immediately I find the relevant options for controlling case sensitivity. Streams can not only be directed from one command to another, but they can also be redirected to files. And that's what I want to show you next. In order to redirect the standard output stream to a file, one uses the larger symbol in Bash. So for instance, if you have a script and you want to redirect all in standard output to a file, you use this syntax here. All error messages will still be outputted on the screen. If the myfile.txt already exists, it will be overwritten by this command. If you want to avoid that, but instead you want to append the output to an existing file, you can use the double larger symbol. If you want to use a file as a standard in stream, instead of the keyboard, you can use the smaller symbol. To best explain this, let's consider the wc-w command, which counts the words in the standard input stream. If I press return here, I am asked to enter a text as a user, and then by pressing Ctrl D, I can finish the command and the wc command tells me how many words were contained in that document. Now, if you want to find out how many words your master thesis contains, you can redirect your thesis file into the wc-w command. Again, trying this out in my terminal, I use wc-w, then the smaller sign to redirect my thesis file into the wc command. And as the standard output, you see the number of words. You can also combine the smaller and larger symbol. So the last example here redirects the standard input into the wc, and the standard output will be saved in a text file. By default, the smaller and larger symbol redirect the standard input and standard output stream. But you can be more specific which stream you want to redirect. And the syntax is shown here. It's a number, 1 or 2 or AND, followed by the larger and smaller symbol. 1 stands for standard input, 2 stands for standard error, and the AND symbol stands for both. So a few examples are shown below. If you only want to redirect the standard output, you can use just the larger symbol or 1 followed by the larger symbol. If you only want to redirect error messages, you use 2 larger, and if you want to redirect both, you use AND larger. Next, let us explore the flow control and command line arguments in Bash. The simplest flow control that we have in Bash are string comparisons and if statements. A simple example is shown below. A string comparison is done with a double equal sign. On the left and right you have the two strings that you want to compare. The notation of an if statement is a little bit unusual in the view of today's programming languages. You need to enclose the case statement with square brackets followed by a semicolon, and it's important here to have spaces before and after the square brackets. Then you use the if keyword before and then keyword after the first line, followed by the statements that you want to have executed if the case evaluates to true. To finish off the code block of the if statement, you use the fi keyword, so it's if reverted. Instead of a string comparison, you can also do an integer comparison. The notation here is slightly different. Instead of the double equal sign, you use the -eq for equal. And then you have the two integers on the left and right of the comparison. It is important to know that integer comparison only works reliable if both variables on the left and right are of type integer. If you're working with variables where you're not sure if it's an integer or string, the safest option is always to convert your variables to strings by using the double colons and then use string comparison, as it is shown here in the first line. Another very important aspect in Bash programming is the handling of command line arguments. As you've already seen, it is very common to pass additional arguments to your command to control the behavior of the program. The ls program might take the -l to show a long version of the files and -h to show human-like sizes. In Bash, you can access these command line arguments through the special variable $, which is of type array. So in particular, if you use $0, you will get the name of the script itself. In this case, it would be ls. If you access $1, you will get the first command line argument, which would be -l. If you use $2, you would get the -h, and so on. Just like for any array variable, you can use also the $@ symbol to access all command line arguments as an array, or the $# to get the number of arguments. Now let's say we want to write an application that takes multiple files as an argument, but we don't know exactly how many. These files could either be provided manually or they could be also provided using the wildcard notation. With the wildcard notation, Bash will automatically identify all files that match this pattern and expand the command line arguments before running the script. So the script will never see the command line argument start.ai, but instead it will see all files that end with .ai as command line arguments. A simple solution for handling arbitrary number of arguments is to write a for loop where we handle each argument separately. So we use the $add array that contains all command line arguments, and we use the for loop syntax to, in this case, run in simulation for each command line argument. And of course, such an approach can be combined to handle more advanced command line options, output directories, and so on. For loops can also be very useful for file management. Consider a simple script whose task it is to remove all temporary files from a directory. First, we use the ls command to find all files that end with tmp. We store the output of that command as an array in the files variable. Then we use a for loop to loop over all these files and execute first a message to the user, followed by an rm command which deletes that file. When implementing for loops, it is often very useful to have a counter variable which is increased by 1 every time we go into the next loop. This can be used, for instance, to show the user progress in the loop and tell the user when the program will be finished. Such a counter can easily be implemented as follows. First, we declare an integer variable called counter and set its value to 0. Then we can use the increment operator, the double plus, on the counter variable. Arithmetic expressions like this always must appear in double brackets. Now we can implement our counter. First we declare our counter variable n and set it to 1. And when we loop over the command line arguments, then we can print, for instance, the number of the command line and its value. Next, let's consider a real example and let's apply some of the concepts that we've learned. In this example, we consider a long command that we would like to make more flexible. This command consists of the application name itself, followed by some command line arguments. We also redirect the standard input from a file called ellipsoid.i, and we use a pipe to redirect the standard output to the T program, which saves the standard output to a file as well as printing it to the screen. Using this command as it is perfectly fine if you use exactly that setup over and over again. But at the same time, there's room to improve the flexibility of this command. In particular, there's 3 areas where we can make this command more flexible. First of all, the command line options here are hard-coded, as well as the standard input file or the configuration file name is hard-coded, and the output file is hard-coded. Second, there's a problem if you execute the command twice, the output file will be overwritten if it already existed. And third, we might want to change the values in that configuration file here before we execute the command. Our task in this example is to write a script that solves these 3 problems. Let's first consider the first problem. How can we change the command line options as well as the configuration file name and the output file name? In case you only want to change a single of these parameters, for instance the CMT option, you can use the following strategy. Essentially what you do is you create parameters with the default values, then you use an if statement where you check if the number of command line parameters is larger than 0. In that case, you use the first parameter to update the CMT value. Now we can execute the original command, but in this time we use the variables instead of the hard-coded parameters. This approach is still limited because you can only control the CMT option through the command line arguments, but I will show you a more advanced parsing of command line options later. The second problem was that if one executes the command twice, then the output file would be overwritten. Of course, one simple solution would be to ask the user to provide the output file as a command line option. But the same problem occurs if the user forgets to change the name of the output file from one run to the next. So a more automatic and safer option is to automatically generate a unique output file. One approach is to create a unique job directory where the output file is stored. This can be done by using the current date as the name of the directory. Here we use our $bracket notation to execute the date command. The current directory is always available in bash through the $pwd variable. Then we use the makedir command to create that output directory, change into that directory, and then we can run our original file. Another trick that we do here is that we create a link points to the directory of the latest run. We do this by first checking if a link with the name latest already exists. In this case, we delete that link. Then we use the ln command to create a new link with the name latest, which points to the job directory. There's some alternative options for creating a unique path for storing the output files. You could use the process ID, which is available through the $$ variable, but be careful because the process ID is not really unique. For instance, if you restart computer, a process ID might be reused. You can also use the make temp command, which is available in bash, which has the specific purpose of creating a temporary file with a unique name. And finally, before overwriting a file, you could check if that directory already exists and exit the script with an error instead. Checking if a path already exists can be done with a -d if test. The third problem that we discussed was that the values of the configuration file could not be edited as command line parameters. This is a problem for some applications which do not take command line options, but instead all the input must be read from the standard input or an input file. I will now show you how to implement a bash script which equips such programs with basic handling of command line options. Essentially, the idea is that we grab the input from the command line arguments, create the correct input files on the fly, and then run the application. What we would like to do is to create a file that contains the text required in the configuration file and potentially substituted some values of bash variables. In bash we can do this with so-called on-the-fly documents, and the command is shown here. We make use of the cut command, which prints the content of a file or from standard in to standard out. We redirect the standard input and feed in a multi-line text of the content that we want the file to have. In that multi-line text, we can also use bash variables. We also redirect the standard output to store the results in the file where we want to have the content. Before we can write the configuration file, we need to obtain the values of the configuration from the user. The command line arguments that we want to support in this case are of this form: -m followed by the value of the m argument, and then -b followed by the value of the b argument. Both of these arguments should be optional. In other words, you can provide only one, both, or none of these arguments. The codeblock that I'm going to show you now is a standard codeblock for parsing command line arguments and is widely used in bash scripts. The solution is as follows. We use a while loop where we continue the loop as long as there's at least one command line parameter in the parameter array. Inside the loop, we check which command line option the user provided. It can either be -m or -b. These are the two valid command line arguments that we support in the script. Instead of an if statement, we here use the case command, which makes the notation a bit more compact. In case option has the value -m, then we again extract the next argument in our argument list and store the value of that parameter in a variable called m. We also use the shift command to remove that value from the command line argument array. We do the same thing for the -b parameter in all other cases, which is marked here by the asterisk. We print an error message and exit the program. At the end, we can print the command line arguments. The double end in bash can be used to execute multiple commands. So in this case, bash first executes this command and then it will execute the echo command. But it will only execute the echo command in case that the first command was successful. So in other words, this line can be equivalently written as an if statement. Similarly, we print the value of b in case b is defined. As I mentioned before, the case statement is standard in bash when passing command line arguments. But you can just as well use if statements. The equivalent codeblock would look as following. After collecting the values of the command line arguments, we can now write the configuration file with the cut command that you've seen before. In my example, I have one parameter that is always constant, followed by two parameters, m and b, that are provided by the user through the command line argument. Finally, we can call our script just like before, but this time we use the automatically generated configuration file instead of the static one. A final trick for this lecture. Often it is useful to print an error message if something goes wrong. The way to achieve that is to add a check if a command has been successfully executed. In bash, there exists a special variable, $, which stores the success of the last command that was executed. If the value of that variable is 0, then the last command was successful, and otherwise the value is non-zero. So simple code for checking if a command ran successful is implemented in the following if statement. We check if the $, value is non-zero. In this case, we print an error message, and we exit the program also with a non-zero error code.